Hello and welcome to PA Academy. So in this video series we are going to be looking at series and parallel connection. So we are going to be looking at what do we mean when we say a connection is a series connection, and what does it mean when we say a connection is in parallel connection. So we are going to be looking at what they mean, and also how to calculate the equivalent value of components when they are connected in either series or parallel connection. So if you are new to this channel, PA Academy, do click on the subscribe button and the little bell icon beside the subscribe button. So with that, let's get started. So now we are going to be starting with series connection, and here in series connection it says in series circuits the components are connected along a single conductive path through which currents can flow. So now let me draw a diagram to illustrate a series connection. So now what we are having here is example of what a series circuit looks like. So this is R1, R2. So if you look at this circuit we are having here, say the components are connected along a single conductive path. So if you look at the movement, if current is to move in this thing, it will go in this direction. So you can see that they are moving in just a single path, So that's what we mean by a series connection. Like this connection now is in series. So the next thing we want to look at is how do we calculate the total value of components in series connection. So when we have how do we calculate the equivalent current or voltage or conductance, inductance, all these components, how do we calculate the equivalent value in series connection? So the next one, which is the number 4 that I want to look at, is conductance. So that is G. So to get the equivalent conductance in a series connection, so that will be 1 over G total is equals to 1 over G1 plus 1 over G2 plus 1 over G3. So plus, then depending on the total number of conductance that we are having in the circuit. So that is it for conductance. So let's look at another one. The one we are looking at is that of inductors. So if you are having inductor in a circuit, how do you calculate the equivalent inductance of the inductor? So to get that, so let's have it as our L total, which is the total or equivalent conductance, is given as L1 plus L2 plus L3 plus, depending on the number. So that means you just add the value of each of individual inductor in the circuit. So with that you'll be able to get the equivalent inductance of that circuit. So let's look at another one, which is that of the capacitor. So if you're having capacitors in a circuit and you want to in a series circuit, don't forget you are looking at series. In a series circuit and you want to calculate the equivalent or the total value of the total capacitance in that series circuit, so that will be 1 over C total. So that is equals to 1 over C1 plus 1 over C2, which is the second capacitor, plus 1 over C3 plus, depending on the total number of capacitor that you are having in the circuit. So with that, that is what I want to cover in this under series. So in the next part of this video, we are going to be looking at that of parallel connection. So what parallel connection is and how to calculate the equivalent value of components in a parallel connection. So if you are yet to subscribe to this channel, please click on the subscribe button and the little bell icon, and then the next video will be appearing somewhere here. So just click on it to watch that of parallel connection. So the first one we are going to be looking at is current. So in calculating the current in a series circuit, the current is the same for what? For all elements. So in writing in that, we are going to have the current, which is I, is the same thing as our I1, is also the same thing as our I2, it's also the same thing as our I3. You know, the currents are the same for all the components in a series connection. So we have, you know, depending on the number of components we are having. So let me just draw a diagram. For example, if we have, let me bring back that drawing. So let me just draw it here. So now looking at this series circuit, for example, where we have this one as our R1, our R2, and our R3, and this is plus. So the current here is the same current we are having here, the same current we are having here, the same current here, and the same current here. So the currents in the components in the series circuit are all same. So that is it for current. So now let's go to the second one, which is voltage. For voltage, we have it that the voltage is same. The voltage is the sum of the voltage drop of the individual components. So what this means is that for us to get the equivalent voltage in a series circuit is the sum of the voltage of the individual components. So that means for us to get, for example, still using this diagram, if you are to get the voltage here, what you are going to do is you are going to get the value of the voltage for this component, the voltage here, that's V1, the voltage here V2, and then the voltage here V3. So what we are going to do to get the equivalent voltage is our V. So that means our V total, that's our equivalent of the total voltage, is equals to V1 plus V2 plus V plus V3 plus, so we can continue depending on the total number of components we are having in the circuit. So that is it for current for voltage. So we are going to be looking at another one, which is resistance. So to get the equivalent resistance in a series circuit, what you just do is you just add the individual resistance, the sum of individual resistance. Now you're still using this series circuit as an example. If you are to get the equivalent resistance for this circuit, what you are going to have is our R total is equals to R1 plus R2 plus R3. That is for this, because we are having 3 resistors, R1, R2, and R3. So the equivalent resistance is the addition of each of the resistance in the circuit. So if you're having more than 3, you just keep adding them depending on the number of resistors that we are having in the circuit. So that is it for current voltage. So we are still going to be looking at more. So if you want to write it down, you can write it down. I want to rub it up so that we can have more space to look at other components.